Hello everyone, welcome back to my YouTube channel. I hope you all are doing well and good. Today, the subject I'm going to be taking over is going to be database management system bearing the subject code 21CS54. So, without any delay, let's get into the video. The contents of the particular video is going to be the introduction, the functional dependencies, the rules for normalization, multivalued dependencies, the differences between functional dependencies and multivalued dependencies, followed by the conclusion. Moving on. Firstly, we have the introduction. So this is going to be the introduction for normalization, which is going to be as follows. So normalization is a process of organizing the data in the database. Normalization is used in order to minimize the redundancy from a relation or set of relations. It is also used to eliminate the undesired characteristics like insertion, updation and deletion anomalies. Normalization itself divides the larger table into smaller and links them using relationships. The last point here is the normal form is used to reduce the redundancy from the database table. Moving on to the next slide. A very important question here, that is, why do we need normalization? The main reason for normalization is that the relation is removing these anomalies. Failure to eliminate anomalies leads to data redundancy and can cause data integrity and other problems as the database grows. Normalization itself is going to consist of a series of guidelines that help to guide you in creating a good database structure. Moving on to the next slide. We have functional dependencies or FDS. So, functional dependencies are going to describe the relationships between attributes in a relational database. They specify the certain attributes that determine the values of other attributes. These dependencies ensure data integrity and redundancy in the database. For instance, in an employee table, the employee ID might be uniquely determined in the employee's name. Understanding functional dependencies is crucial for effective database design and normalization. So an example for this is, consider a relation R with attributes A, B and C. If for every unique value of A, there is only one corresponding value of B, then we denote it as A, an arrow marked towards B, or A which relates to B. Moving on to the next slide. We have the rules for normalization. So the first one being first normal form or 1NF. In 1NF, each table attribute holds only atomic values or indivisible values, avoiding multivalued or repeating groups. This simplifies the data organization for efficient storage and retrieval in DBMS. Next one being second normal form, also denoted as 2NF. 2NF is going to ensure non-prime attributes are fully dependent on the primary key, eliminating partial dependencies. This streamlines the table structure, reducing data inconsistency and enhancing the DBMS performance. Following which we have third normal form or 3NF. 3NF removes the transitive dependencies, ensuring each attribute directly contributes to the primary key. This minimizes the redundancy and improves the data integrity, making the database more reliable for various applications. Moving on to the next slide. We have multi-valued dependencies or MVDs. Multi-valued dependencies or MVDs are constrained in relational databases. They describe the relationships between sets of attributes. MVDs are going to specify that the value in one set determine possible values in another set. These dependencies capture scenarios where attributes exhibit multiple values for each combination of values in other attributes. Unlike functional dependencies, MVDs handle cases of multiple possible values for each combination of values in the other attributes as follows. Moving on to the next slide. These are basically the key concepts that come under your MVDs. So these are trivial and non-trivial multi-value dependencies. So here trivial MVDs are dependencies where one attribute or set of attributes functionally determine another attribute or set of attributes within the same relation. A relation here is going to refer to a table. Next one being non-trivial MVDs. These are dependencies which are going to express significant relationships between set of attributes where the determination is not immediate from other dependencies. The next key concept here is going to be 4NF and BCNF. So the definition for 4NF is going to have no MVDs, whereas your BCNF, here BCNF is going to stand for Boy's Code Normal Form. This is going to have no non-trivial functional dependencies where the determinant isn't a super key. The importance of this is going to be in order to ensure minimal redundancy and dependency preservation. And conversation here is going to decompose the relations to eliminate anomalies and achieve normalization. Okay, so this slide is going to deal with the conversion to 4NF and BCNF. So here you're going to be decomposing the relations to eliminate redundancy and comply with normal forms. You're going to ensure the preservation of dependencies and lossless join properties. Third one being techniques like dependency preservation and relation decompositions are utilized. The last point being enhancing the performance, integrity and facilities that are going to be efficient for management of the database itself. Moving on to the next slide, we have the differences between the FDs and the MVDs. So first I'm going to be talking about the FDs, then I'm going to move on to MVDs. So first one we have FDs. Here, these are going to describe the relationships between single attributes in a relation. Second point here is representing the dependencies where one attribute uniquely determines another attribute's value. Third one, here it is going to be used to ensure data integrity by eliminating the data redundancy and the anomalies. The fourth one being they are simpler and more common in database normalization processes. And a good example for this is in a relation with attributes A, B and C, if A determines B, then it is determined as follows, that is A an arrow mark towards B. Now I'm going to go on to MVDs. So this is going to describe the relationships between sets of attributes in a relations. These are going to represent dependencies where one set of attribute is going to determine another set of attributes values rather than individual attributes. The third point here is going to be used to model more complex relationships where attributes have multiple values associated with them. The fourth point here is they are less common than FDs in database normalization but are important for specific cases involving non-traditional database structures. A good example here is in a relation with attributes A, B and C, if A determines a set of values B and C, then it is represented by an A arrow mark towards B and C where B and C are going to be enclosed in curly parentheses. So these are going to be some of the key differences between FDs and MVDs as follows. Moving on to the next slide, we have the conclusion for this particular video. So the recap of the importance of normalization here is normalization itself is a very vital process in database design, ensuring data integrity by minimizing redundancy and dependency issues. It is also going to simplify the data management, reduce anomalies and support scramble efficient databases. Next, we have the summary of functional and multi-valued dependencies. Functional dependencies itself is going to describe the single attribute relationships, aiding in normalization to eliminate redundancy. Whereas multi-valued dependencies are going to address more complex relationships between set of attributes, crucial for specific data structures. Both are essential for ensuring data integrity in database design. I hope that you understood all the topics that were covered in this particular video, right from FDs to MVDs, the differences between them, the few examples that were taken care of here, as well as the key concepts that came under both FDs as well as MVDs. So thank you for watching the video and I hope you enjoyed it.